Good morning. Today I am to discuss about antibiotics, quinolones antibiotics. So, the first quinolones that was discovered is nalidixic acid. I already sent the PDF to you. So, open your PDF. So, nalidixic acid, it is the first quinolones that was discovered, and it is effectively act against gram-negative bacteria and mainly used in urinary tract infection, UTI infection, that is caused by E. coli. Okay, and the chemically nalidixic acid is 1,8-naphthalopyridine derivatives, and that's all effective against gram-positive bacteria. There are some disadvantage of first generation's quinolones. Number one is the very poor solubility. As it is very less soluble in biological fluid, then the bioavailability of the drug is very poor and cannot reach to the perfect conditions. There are so many side effects, and another is it strongly bind with the metal ions and produce the insoluble complex. So today, first generation quinolones are not used due to this disadvantage, and to minimize this problem, the second generation quinolones were discovered, and this is called the fluoroquinolones, second generation quinolones or fluoroquinolones. And the basic difference between quinolones and fluoroquinolones or second generation quinolones, that is the at position 8. In case of first generations, the position 8 is the nitrogen, and in case of fluoroquinolones, this is the carbon. So chemically we can say that the basic structural difference in case of first generation, that is nalidixic acid is the 1,8-naphthalopyridine, whereas fluoroquinolones is the benzyl 2-hydropyridine conjugated with 2-hydropyridine. So the important structure activity relationship for fluoroquinolones, that is there are three essential moiety in fluoroquinolones antibiotics. Number one is the 4-oxo moiety at C4 at pyridine nucleus. 4-oxo, that is the keto functional group. That is it produces the strong hydrogen bond with the receptor, and it is the essential moiety. And the second essential moiety is the carboxylic acid, that is at C3 of pyridine ring, conjugated to hydropyridine ring, and this is it will produce the strong iodine bond, that is this carboxylic acid is protonated in the biological fluid and strongly bind with the receptor by ionic bond. And the third is the benzyl ring conjugated with the 2-hydropyridine ring, that is the planar, and it will produce the strong hydrophobic interaction or van der Waals interaction with the receptor. So these three parts are very, very essentials. Number one, 4-oxo, number two, 3-carboxylic acid, and number three, pyridine nucleus. So 1,4-dihydro-4-oxo 3-pyridine carboxylic acid is the main importance in fluoroquinolones, and this pyridine must be conjugated with an aromatic ring. Here in case of fluoroquinolones, the conjugated aromatic ring is benzyl ring. Next, carboxylic acid, it is very important, and the isosteric replacement of nitrogen for carbon atom at position 2, that is cinnoline, and position 8, that is 1,8-naphthalopyridine, that retention of the antibacterial activity, and any substitution at position 2 is completely loss of activity. The bicyclic ring, that is benzyl and 2-hydropyridine, is not essential for biological activity, but substitution on 6 positions of pyridine ring with heterocyclic ring or any aromatic ring will gives a potent drug. This is why 2-hydropyridine is always conjugated with aromatic benzyl. The 3-carboxylic acid may be substituted with isothiazole moiety. So we can say the 3-carboxylic acid is the bio-isostar of isothiazole, because replacement of isothiazole in place of carboxylic acid, this derivative is 4 to 10 times potent than ciprofloxacins. Why more potent? Number one is the NH proton of isothiazole is more acidic in nature, and it mimics the action of carboxylic acid, and the solubility of the drug is also increased when isothiazole substitutions occurs. And the isothiazole conjugated with 2-hydropyridine is more aromatic in nature, and due to this more aromatic in nature, they strongly bind with receptor by hydrophobic bond rather than carboxylic acid. So previously I said X may be the nitrogen in case of enoxacin, that is the less potent drug, and X may be the CH in case of second generation, is the most potent drug. The nitrogen at positions may be substituted by C2H5, that is the ethyl. Mainly all the drugs, that is the first generation and second generations, the N of pyridine, the nitrogen of pyridine, that substituted by C2H5, and sometimes it is substituted by cyclopropyl or dibromophenyl. Group, because substitutions with the cyclopropyl group always increase the ring strain and here increase the affinity towards receptors. Next, sometimes this cyclopropyl ring substitution is more potent rather than the other substitutions. When this C2H5 or cyclopropyl group is replaced by oxytocin group, that is also effective in gram-negative bacteria as well as gram-positive bacteria. So oxytocin derivative that act both gram-positive as well as gram-negative bacteria. The oxytocin ring helps in the penetration of the drug through the outer membrane of gram-positive bacteria. This is why they are very active drugs and very active derivatives. The 6 positions should be substituted with fluorine. This is why all the second generations are called fluoroquinolones. At position 5, it may be substituted by electron withdrawing group like amine group, and which improve the pharmacokinetic parameter of the drug. What is the pharmacokinetic parameter? That is the ADME of the drug. At position 8 of second generation quinolones may be substituted by some halogen or methoxy group, and at position 7 must be substituted by piperazine ring, number 2 N-methyl piperazine, number 3 pyrrolidine. Why these substitutions occurs? Because piperazines also increase the solubility of the drugs and imports in the pharmacokinetic parameter of the drugs. So from the different structures you can see the difference between first generation and second generation, and the structure activity relationship of quinolones is very, very important. Next, norfloxacin, that's all we know, that is given in diarrhea. The basic difference between norfloxacin and enoxacin. What is enoxacin is the first generation and norfloxacin is the second generation. The basic difference in position 8. In case of enoxacin, that is nitrogen, but in case of norfloxacin, that is CH. So you have to write, or you have to remember all the structures through the difference of the moieties or different group at different positions. What is the difference between norfloxacin and ciprofloxacin? You can see the structure, the basic difference, the substituents at pyridine nitrogen. In case of norfloxacin, it is C2H5, but in case of ciprofloxacin, it is cyclopropyl group. There are so many other drugs like pafloxacin, ofloxacin, lomefloxacin. One important is the ofloxacin. Ofloxacin, that is the racemic mixture, dextro plus levo, both forms there, but only active form that is more potent, that is the levofloxacin. Levofloxacin is the levo isomer of ofloxacin, that is that is capital S configuration. So levofloxacin is the capital S levo form of ofloxacin, that is more potent than ofloxacin. There are other drugs, that is lomefloxacin, sparfloxacin, gatifloxacin, moxifloxacin. Gatifloxacin nowadays not used. The basic difference between these drugs, all the structures contain cyclopropyl except lomefloxacin, and moxifloxacin at C7 it contains pyrrolidine ring. At gatifloxacins, it C5 contains amine group. In moxifloxacins, both contains the at 8 positions the methoxy group, and in lomefloxacin, that is fluorine group. So here is the structure activity relationship of quinolones antibiotics. Next, it's also very important, its mode of actions. All the quinolones antibiotics bind to the A subunit of deoxygenase, that is topoisomerase 2 type of enzymes, and it prevents the binding of substrate to the active site of deoxygenase. Absence of formation of enzyme, and here it blockade of unwinding of double-stranded DNA into the single-stranded structure. This is why it prevents the synthesis of DNA and as well as inhibit the bacterial protein synthesis. This is the main mechanism of quinolones antibiotics. Once again, I am sharing this mechanism. Actually, all the quinolones, through the diagram, if follow the diagram, all the quinolones antibiotics, it binds to the A subunit of deoxygenase or topoisomerase 2 type of enzyme, and prevents the binding of substrate to the active site of deoxygenase, and absence of formation of enzyme or substrate complex, it block the unwinding double-strand DNA into the single-stranded structure and prevent the synthesis of mRNA as well as inhibit the bacterial protein synthesis. And the next part I want to discuss next antibiotic, that is tetracycline. It is also a very important antibiotics. Tetracyclines, that is the tetracyclic ring system, and it is designated, I already mentioned in the PDF, ring A, ring B, ring C, ring D. The ring A, the three essential moieties on ring A, that is the ammonium moiety, number 2 carbonyl methane, and number 3 phenol diketone. Okay, so these three ionizable, these three moieties are ionizable part in tetracyclines. So the three ionizable part is number 1 ammonium moiety, number 2 tricarbonyl methane, and number 3 phenol diketones. And this is why tetracycline cannot be given with metal ion like calcium, iron. They will produce the chelating agents binding with the metal ions and produce a complex which is not soluble in biological fluid. So tetracyclines, that is cannot be given different foods like meals, iron tablets, because they binds with these metals and produce the chelating agents. Another part is there must be some ketoenol tautomerism between carbon 1 and carbon 3. This is why there will be no substitution at this point. If any substitutions occurs, then activity becomes zero. Next, already said C1 and C3, that is the ketoenol tautomerism may occurs, and this is important for antimicrobial activity, and C1 and C3 cannot be substituted. Another important part is the epimerization occurs at C4, which is also responsible for increasing the potency of the drug, and the C2 amide linkage that is can be substituted by different substituents, and which improve the biological activity. The 10 hydroxy is very essential, and there also a ketoenol tautomerism between 10 and 11 carbon. The strong acid and the strong base inactivate the tetracycline nucleus. The presence of 6 hydroxy is responsible for deactivation in acidic medium. Removing of this 6 hydroxy, you can see the removing of the 6 hydroxy increase the lipophilicity of the drug as well as increase the stability of the drug. The C7, that is R1, the C7 that is R1, that is substituted with electron withdrawing group, that is amine or any halogen. The aromatic ring D cannot be substituted except electron withdrawing group at C7, otherwise complete loss of activity. So we have to intact this ring D. The stereochemistry of hydrogen at C4A and 12A, C12A should be cis configuration. What is 4A and 12A? That is the conjugated point of ring A and B. Ring A and ring B conjugated at 4A and 12A positions, and this proton should be cis configuration. If it is trans configuration, then activity becomes zero. So this is all about tetracyclines. There are so many derivatives of tetracyclines. Number 1, tetracycline, chlortetracycline. What is the basic difference between tetracycline and chlortetracycline? That is at C7 position or R1. In case of chlortetracycline, it is Cl and improve the activity. And oxytetracyclines, that is the difference at R4 position, that is hydroxy group, whereas in case of tetracyclines, R4 is hydrogen. The importance other drugs is that oxycycline, minocyclines, and the electron withdrawing group like chlorine, amine, that must be substituted in R1, and it in case of chlortetracycline and minocyclines, they contain the electron withdrawing groups. This is why they are more potent drug. Thank you.